Okay, welcome to our topic on electric current. This is the lead into our circuits, the circuits part of our electricity unit. Now, the whole reason we've been learning about electricity and electric charges and forces and electric fields and electric potential is because we use electric charges to quite literally power our modern everyday life. Almost everything that we do is thanks to our knowledge and use of electric charges to do what we need them to do. The main application of electric charges, what we use them for, we use them to provide energy. We use them to transport energy from one place to another. In order to effectively provide this energy, we channel charges, or current, it's just a whole bunch of moving charges together, through conductors. Okay, remember, a conductor is something that allows the easy flow of electric charges. The definition of electric current is the movement, if I can spell, of charges past some point over a period of time. There's an equation for calculating electric current, and it is given right here in the reference tables. I equals delta Q times T. I equals delta Q divided by T. And delta Q doesn't mean the charge is changing. All that delta really refers to is how much charge passes a point. And it's in coulombs. Okay, so it's how much charge has passed a certain point over a period of time. The units for this, well, since charge is given in units of coulombs, time is in seconds, we have coulombs per second, but there is a better unit for that. It is known as the amp or ampere, named after the guy who found it. So you might see capital A, you might see amps, you might even see the whole word written out, amperes, with a nice little accent grave on the E. Current is scalar. Doesn't really have a direction. I mean, you could say that current is flowing in this direction or this direction, but it doesn't really have a direction the way that we use it. You can think of current like, imagine standing on the side of a highway and counting the number of cars that go past you per minute. During the day, maybe during rush hour, there's going to be a lot of cars passing you per minute, maybe in the hundreds, okay? So like 100 cars per minute. At nighttime, at like 3 or 4 in the morning, you might have like 1 or 2 cars passing you per minute. The current of cars is much greater in the daytime at rush hour than it is at nighttime in the wee hours of the morning. Okay, so we would say that the current is bigger for daytime as opposed to nighttime. And in that case, we're counting cars per minute. You can think of electric current as the same thing, except instead of cars, we're counting charges. Okay, my personal favorite analogy for this particular area is think about like the Boilermaker. If you're going to go watch the very beginning of the Boilermaker when everyone's all bunched up together, you are standing on the sidewalk and you watch, thousands and thousands of people pass you per minute. It's like watching a bunch of electric charges pass you. So, quick example, if 5 times 10 to the 18th electrons pass by a certain point in a wire in 1 second, what is the current? First of all, we need to convert this amount of charge to coulombs. Right now, it's 5 times 10 to the 18th electrons. That's elementary charges. We need to convert to coulombs. 5 times 10 to the 18th E. Let's see, we know that 1 elementary charge is 1.6 times 10 to the negative 19th coulombs. 5 times 10 to the 18th times 1.6 times 10 to the 19th, 0.8 coulombs. We can calculate the current by plugging into this equation, I equals delta Q times T. Delta Q is the amount of charge that passes, that's 0.8 coulombs, divided by 1 second. The current, I, is therefore 0.8 amps. Okay, very easy to calculate current, just make sure that you have this in C. Now, how do circuits, which are how we transport electric current, how we transport those charges that make up the current, how do they work? Most circuits make use of wires and other electrical devices to deliver energy. Since the wires are made of metal, they have plenty of extra electrons that can be used in a circuit. You remember from chemistry something about for metals, they have this thing called the sea of electrons, where the electrons are not very tightly held to their parent atoms. That's what we're making use of here. The electrons are so loosely held that it's very easy to apply an electric field to those electrons and get them to just kind of move down the wire, jump from atom to atom, and that's what creates a circuit. Now, as far as the nitty-gritty of circuits, every circuit has three basic components. No matter how complicated it is, every circuit has three basic components. You have a power or voltage source. You have an energy consumer, or a power consumer, or a voltage consumer, whatever you want to call it. And you link those two with wires. Let's talk about the power and voltage symbols and sources first. On your reference tables, page 4, right under the equation part, you'll notice that there is a table of circuit symbols. For power or voltage source, we're just going to look at the first two, a cell or a battery. Notice that a battery just looks like a couple of cells stacked on top of each other, and that's exactly what it is. A battery is just like an extended cell. You do need to know how to draw these pictures, these circuit symbols, because you will be asked to draw circuits on homework and on quizzes and tests. So you should know what each of these symbols stands for. So there's a cell, there's a battery. Each of these things, the point is that it stores energy. Okay? Matter of fact, if this is a battery, I usually just say battery because that's what we're most familiar with, then that means that it has a positive and a negative terminal to that battery. And we know that between the positive and negative terminal, there is a potential difference. What that boils down to is if a charge were to go from one side of the battery to the next, it will lose some energy. Energy per charge difference. So remember, potential is like energy, but it's not exactly the same thing. Now, you might be asking, well, if there's a potential difference between the two parts of the battery, how come the charges don't just go from positive and negative? There's restrictions, okay? Batteries are designed so that charges cannot flow inside the battery. They have to go through these external wires. Okay, so let's see. Energy consumers. Things that use up energy and bring it someplace else. Those are these three things down here: a resistor, a variable resistor, and a lamp. Okay. All of these things, whether it's a resistor or a variable resistor or a lamp, they are things that use the energy for some purpose. So these use the stored energy from the battery for some purpose. And when they use that energy up, what that causes to happen is that the voltage, which again, remember, is the energy per charge, decreases. So if you have a resistor in a circuit, it will use up some energy. It will take that stored energy that is being brought to the resistor by those electric charges. They each have some energy. They bring it to the resistor, and it turns that electric potential energy that they have into, for a resistor, heat energy. After a while, running in a circuit, a resistor will get warm. You can actually feel this. A variable resistor is the same thing as a resistor, but it can change what's known as its resistance. Okay, you can change the resistance of a variable resistor very simply. Whereas normal resistors, it's kind of like depending on what the voltage difference is and what the current is, they give off there's a set ratio for what the voltage difference to the current is. For a variable resistor, you can actually control that a little bit. A lamp gives off energy as heat, just like a resistor and a variable resistor do, but as you know, they also give off light energy. And then, most importantly, connecting the power source to the energy consumer are wires. Okay? Without the wires, you don't have a circuit. There has to be at least one complete path for charges to go from one terminal of the battery to the next. So what happens is, so we have charges that flow out from the positive terminal. Here's the current. I'm just going to use little arrows to show it. When they flow out from the positive terminal, you can think of those charges as having lots of energy. They have electric potential energy. What ends up happening is there's an electric field set up in the circuit that the electric charges want to get away from from the same type of charge. So imagine if this is the positive terminal, you can think of a little positive charges flowing around. They want to get away from this positive side of the battery. Okay, that's an electric field. They're getting repelled. So they carry that electric potential energy that they have with them to the energy consumer. At the energy consumer, what happens is they give up that energy. What really happens is it's kind of like difficult for the charges to get through the energy consumer, so they end up releasing that energy. They don't just stop, they don't disappear, they flow back through the wires to the other side of the battery, the other terminal, and down here they have low energy because they gave that up. Okay. Now, the charges don't just keep flowing around. They kind of start over on the positive side. They end up on the negative side. They don't go from negative to positive. They don't just make a complete circuit of it, or they don't make a complete loop of it. But basically, you can think of the charges just going all the way through. Okay. Now, some other possible parts to a circuit are these three symbols in the middle: a switch, a voltmeter, and an ammeter. So here's a switch. I'm going to draw it in the open position. If you have a closed switch, I just kind of draw a line, but I put two little circles here to show that there is a switch there. And quite obviously, a switch controls. Let me move this up a little bit. The switch controls if a circuit is on or off for the whole circuit or even just part of the circuit. You will see this symbol, a circle with a V in the middle. This is a voltmeter. And what a voltmeter does is it measures the electric potential difference between 2 points in a circuit. Remember, voltage is potential difference, okay? The difference in potential between 2 points. Since an electric field is being set up inside the circuit, there's going to be a potential difference between 2 points in that electric field. And then finally, we have, if it's a circle with an A, that is known as an ammeter. And that measures the current at some point in a circuit. There's something that might be confusing you right now, and it's something that we've talked about since the beginning of the electricity unit. We have said since the beginning that the type of charges that are actually usually able to move around and have less restrictions on them are electrons. Protons, positive charges, are usually locked in the nucleus. They can't move. So it might have been kind of confusing to you when I said that charges flow out from the positive terminal and into the negative terminal. Because if you think about it, the positive terminal obviously is positively charged. Electrons are negatively charged. Why wouldn't electrons want to go into the positive terminal? And the answer is, that is exactly what they do. But we actually look at electric current from a different perspective. In reality, electrons move from the negative terminal of a battery to the positive terminal. In reality, electrons leave this side because this side is more negative. The electrons get repelled this way. They go here. They go through the energy consumer, go into the positive terminal. However, when we discuss circuits, we actually pretend the opposite is true. We pretend that the moving charges are positive and that they are instead moving from the positive to the negative terminal. Now that seems a little confusing. You're like, why would we ever pretend this? Well, number one, it's a lot easier to think of positive charges moving than it is of negative charges moving. The less we have to do with negative charges, the better, because we're just more used to positive numbers, positive charges. That's fine. The reason that this works out is because it's kind of like in double negative. If you think of the way we have this drawn right now is positive charges moving clockwise, negative charges would move counterclockwise. It's like those two differences kind of cancel each other out. We still get the same effects. Historically, what happened here is that when we first discovered electric charge, and we discovered there was two types, we just called one of them positive, one of them negative. Before we knew which type was actually flowing in the circuits, we just assumed it was positive charge. It turned out to be negative charge. So going back, if we could have just assigned the other type of charge to be positive and the other type of charge to be negative, like if we just made the distinction that electrons have positive charge, protons have negative charge, we wouldn't have this particular problem. But we didn't do that. There's no point going back now and trying to fix everything. We're just going to assume that positive charges are what flows around the circuit. Okay, now what I want to do is I want to show you an amazing tool for building your own circuits. We might build some circuits in person in class, but there is a web app that allows you to virtually build circuits that is absolutely incredible. You can access this. It's very easy to find. Let me get this in, okay. PHET, this is a simulation database that you have used before. Circuits. And you're going to go to Circuit Construction Kit DC from PhET. Click on the play button. We're going to get that. There we go. Okay. We're going to go just right to the lab. And it brings up basically a sandbox. Okay. This is just an open thing for you to play around with. Let's get this to focus a little bit better. You'll see over on the left-hand side there are a bunch of different things you can put into the circuit. Wire, battery, light bulb, resistor, switches. We can put in other stuff, but we're probably going to stick mainly to those. Fuse, other batteries, light bulb, resistor. Okay, yeah, there's just kind of fun stuff you can throw in there. Dog for some reason, apparently. You can switch from the actual picture of the object to what the circuit components look like. Their light bulb picture is different from ours, but that's fine. You can zoom in and out down here. Over on the right-hand side, it says show current. We can either do electrons or conventional current. That's what I was talking about with assuming positive charges are flowing. Labels for everything, and values, which we're not going to click on just yet, but we will later on. You can also bring in a voltmeter or some ammeters if we click on advanced. We will eventually need to know about wire resistivity, but not quite yet, and battery resistance we won't need to know yet. So this is nice because you can just kind of click and drag, and you can orient everything the way you want them to. So I'm going to put in a battery and a resistor. I'm going to connect them with wires. I kind of like to make everything nice and square just because it makes it easier to see. It's very simple, and this does also work on phones, by the way, so you could even do this on phones. I have tried to advocate for you guys, when you are doing homework for this circuits part of the unit, like you could literally get all the answers by just building these simulations. You almost don't really have to know anything. If you can build these circuits, you can get all the answers that you might need. Watch what happens when I finally connect these two last wires. Notice that nothing is flowing in the circuit right now because I don't have it connected. As soon as I connect it, now those electrons are flowing. Now, I can switch back and forth between electrons and conventional current. Notice that these are just arrows that are flowing in the opposite direction. Notice the arrows are flowing counterclockwise. The electrons are flowing clockwise. You're going to get the same exact readings no matter what. Now, I could throw a switch in there to when I open the switch, it breaks the circuit up. When I put the switch on, it causes this current to flow. I don't really care too much about that. We're going to go back to conventional current. I can bring in a voltmeter. Remember, voltmeter measures the potential difference between 2 points in an electric field. I connect the probes across some part of the circuit, and it tells me the potential difference, the voltage. -9 volts. Let's do another one. Again, -9 volts. Okay. Anyways, that can measure the potential difference for us. I also have access to some ammeters. I'm going to use the cheating ammeter right here. This just hovers over and it'll tell you the current in the object. This isn't really how an ammeter works. Really, we would need one of these, but I'll show that to you later on. So this is a really neat little sandbox application for you to be able to build your own circuits and see how they work. This works exactly the same as if we had some kits, and we do have some kits in the classroom, but this is almost easier to do. It requires, almost less time to wire up. So this is really, really neat stuff. I'm going to put this back down for just a second. And we're going to flip over. We're going to talk about resistance. Okay, electrical resistance. Now, if you had some wires and they're only connected to, if only wires are connected to a voltage source, like a battery, the current created will likely be way too much for the wire to handle. The charges are going to move way too fast. And they're basically what's going to happen is you're going to create a short circuit. Short circuits aren't good. Short circuit looks like this. I'm going to reset this. I'm going to go back to the simulation for a second. Imagine if I had a battery that was connected to itself with wires. Okay, watch very carefully what happens to the battery once I connect this. That doesn't seem good. The battery seems to be on fire. Look how fast those charges are moving, okay? If I disconnect this, it's fine, but as soon as I connect it again, battery turns back on fire. What's happening is there is nothing to dissipate the energy of those charges. They are moving so fast through the circuit that they are actually causing an explosion or a fire in the circuit. And this is literally what happens. Basically, those charges move so fast they cause the circuit itself to heat up and either explode or catch on fire. That's what a short circuit is. You don't want that. If I'm drawing symbols of this, it would look like this. Here's my battery, and here are my wires, and I'm just connecting the battery right to itself. Battery connected to itself. Energy is transferred too fast, and what happens is the circuit explodes or catches on fire. We don't want short circuits. Instead, what we need to do is we need to put something in the circuit that will resist the current. Something that will decrease that very fast, very rapid flow of electric charges so that we can make the circuit safe and useful. Anything you put in a circuit has this property that will cause the flow of charges to go down. It's called resistance. Anything you put in a circuit, even wires have some resistance, but especially resistors, lamps, variable resistors, they all have this property called resistance. The resistance of a certain part of a circuit is given by this equation. And this is again from the reference tables, R equals V over I. Right here, R equals V over I. V in this case is the potential difference before and after the object that you want to know the resistance for. Basically what that boils down to is how much energy is used per charge. Okay, that's the potential difference across, we would say potential difference across that piece of the circuit, that certain part. I is the current flow. How much current is flowing through the object, through that piece of the circuit. The resistance of many of the objects we will look at this year, like resistors and lamps, is a set ratio. If there's more current flow, there is a bigger potential difference. There's a bigger loss of energy, but still the resistance of the object will remain the same. And we'll see that in some labs. Objects with resistance, what they basically do is they use the energy that the charges have. The charges bring them their electric potential energy, and they use it for some other purpose. Resistors get hot, they give off heat energy. Lamps get hot and give off light energy. Another way of thinking about it is that charges must work or use energy to get through the object, the piece of the circuit. Okay, think of like a bottleneck on a roadway. Okay, it decreases the flow of cars that can go on the roadway. Like if one lane is shut down, and basically those cars have to work to get through. They give off some energy as they're going through. Last thing before we call this video, the units of resistance. Potential difference is measured in volts. Current is measured in amps. So you could say that the units are volts per amp, or this symbol, kind of like a horseshoe symbol, and that's known as an ohm. And finally, resistance is scalar. It does not have a direction. So any circuit component has some resistance built into it. Resistance is the ratio of the potential difference before and after the object divided by how much current is flowing through it. So basically, how much energy per charge is being used by that object divided by how much current there is, how many charges are flowing through the object. When we come back, we'll talk about a few rules for circuits, and we'll also talk about wire resistance.